Hello, welcome to the class ECE317 Digital Signal Processing. Today is the 14th week. Actually, this semester almost done, right? So ECE317. This is the 14th week, Monday's class. Actually, this is the last week with new material. This is the 14th week. Right? Now it's Monday and then Wednesday. These 2 days we have some new material. And then Friday we will have a review for final exam. And then in the 15th week there's no class, but we have Zoom meeting for questions. You can say there are some office hours, but actual office hours we will use the class time Monday, Wednesday, Friday. The class time it is 10 to 11 a.m. and then Wednesday 4 to 5 p.m. This is a normal office hour, right? Normal, right? Okay, then the 16th week there will be the final exam. Our exam. Okay, final schedule. Okay, the second one completely. Okay, yeah, we have all of this. ECE317. That's a month. May. Oh, this we have 3. Okay, 317. See, they have 3 sessions. The first 2 sessions they are the lab sessions. We do not have exam for lab. We only have exam for the lectures. It's Monday, Wednesday, Friday. So it's here. Friday. Okay, let me write it. It's Friday. It's May 7th from 10:30 to 12:30. 12:30 is p.m. May 7th. Alright. So don't forget the time. The way will be similar with the midterm exam. I will post the problems in the Blackboard, also send the email with the problems, then give you a time limit. You try to finish. Here's a 2 hours, right? 2 hours, and I give you the similar with 30 more minutes for submit. For submit, so you can submit by 1 p.m. Okay, so this is the final exam time. Okay, then today what we will do? We will discuss the filter design. Actually, you should already have some lab experiment about the filter design. And here I just gave you a kind of brief review about the filter design. This is a kind of very, you need a practice. So a lot of details. During your practice, you should know a lot of details. Here I just give you some ideas about how to design the filter. The first one, the result of the first method is a FIR field. We want this one, required field. I use just one example to explain it. Like this is a low pass filter. Low pass filter. And this is the ideal one, right? This is 1 here, and this is 0. From 0 to pi, this is omega. From 0 to pi, we have a cutoff frequency omega c. When omega is smaller than omega c, here will be just 1. And when omega is larger than omega c, this will be just 0, right? This is a frequency response. So we want a field with frequency response looks like this. But of course, we cannot really get this kind of thing. We can only have an approximate. We can work like this. We perform the this is inverse. We go to the time domain. We have inverse dtft. Then we have let will be a h of n, right? This is a capital H, not a lowercase h. And this one, it will be something depend, right? Here I just write something. Maybe it varies depending on what is the h, right? Something like this. Okay, this is h of n. Usually you will have infinite values. That means this will be IIR field. This will be IIR. This is the required one. But we will have a FIR, approximation. Okay, how to do it? We just pick some of it. Right? This one is IIR, so you have infinite non-zero values in this impulse response. We pick some. For example, we pick this. Then we call this as a window. It's a window. We just pick the value inside this window. Then we can have one looks like this. We also need a shift, right? If the first element is here, we need to shift to the positive side. You can also pick a window. You start from all the values in the positive side, then you shift to the left side. So by shift, you need a shift. Then you will have things look like this. Just no this part, just like this. We will have this. This one, it is FIR causal field. We use this. This is a H hat of it. This is our result. Of course, because you only pick values from this window, you will lost some information. So the result is not exactly as same as that. So you need to check. You use DTFT. You will have a spectrum of this one. Usually not so straight line like this. It will be something looks like this. Something looks like this. From 0 to pi, the h hat of e to the j omega magnitude. Oh, here is also magnitude. Sorry, but as ideal one, it will be the same. But this one usually the magnitude will be different with this function itself. The function itself will be complex function, complex value. And then here we have something. We need to separate the part like this. Okay, this part we call it a passband. Passband. In passband, the value is close to 1. Like this is 1. It's close to 1. Not exactly the same, but it's close to 1. And this part we call this is stop band. Stop band. In stop band, the frequency response, the magnitude will be close. A value will be close to 0. Not exactly 0. Maybe it is 0, but depends, right? Close to 0. And then we have this part. This part is between these two. It is neither passband nor stopband. It passed some, but not really stop. So not really pass, right? It's not. We call this is a transition band. Transition band. Okay. So by this way, you will have edge hat. This is a FIR culture field. Its frequency response, the magnitude response will look like this. And you will check your requirement. Your requirement, yeah, of course you want this ideal one, but you can't. You will have some, for example, here you want 5% different with one, and here you want like 3% with 0, and you will check whether this one satisfies your requirement. Right? Here's 5%, here's 3%, and here this transition band, it is around WC, but not too large, right? That depends your requirement. If this work, you get it. If this one do not satisfy your requirement, you still make more. You need to pick more values. Right? You pick some, you get approximate. You pick more, then you have more accurate approximation. So you pick more point from here. You increase the size of the window. And here I said the window start from some negative value to positive value. But the common used window just start from 0 to some end. So the commonly used commonly used window just from 0 to some m, and you increase m. The other side, you do not use the negative sign, just use 0 to m. Use 0 to m. Yeah, the common used window just use 0 to m, and you can increase m to get the edge hat has better approximation with these. Like here's a low pass filter. You can choose different filter. Here's a low pass filter. Maybe you want a band pass filter or high pass filter. You can work in similar way. You perform inverse DTFT. You have frequency response. You have impulse response here. Then you pick some value from a window, and then go back to see whether it works. If not, it doesn't work. If it works, that will be fine. If it doesn't work, then just increase the size of the window until you get your result. And people usually like just use 0M as a window, because if you use this one, you do not need to shift. Okay. If this is 0 to M, then just 0 to M. You do not need to shift. You just pick it, put it here. That will be fine. Okay. And when you want to change, you just change this M. Increase the value of M. You do not need to consider both sides. If you use both sides, then this side you increase, the other side you will decrease, right? You need two sides. Yeah. Now you just use one side. That will be fine. Okay, this is the first method. Second one, we try to use the continuous times field. From continuous time field. Then find the discrete time field. Now we'll work like this. Because actually we already have several different classes of continuous time field. They can be applied in different situations. And then we just define the discrete time one based on continuous time field. To do this, actually we still have several methods. This is method 1. Method 1 is impulse invariance. Impulse invariance method. The idea is like this. For the continuous times field, suppose this is a edge of C, HC of S, Then this side I want h d of e to the j omega. We try to design this one from hc. hc, if hc of s is some 1 over s plus a, then this one we have a Laplace transform. This one for continuous time signal, we have a Laplace transform. Laplace inverse transform, we will have hc of t, it is e to the negative at times us of t. So it looks like the graph like this, 0, then e to negative at, things look like this. And then we take symbol. Take symbols. Step is t. We need a step. Every step t we take a symbol. Then we have h d of n, which is e to the negative a t times n, then us of n. Actually, this is just u of n, a unit step. In continuous case, people like to put the us of t for the unit step. I use the same notation. Yeah, in our course usually we just use u of n, right? u of n. You have this one. Alright, this one we do the z inverse transform. It will give us what? It will give us 1 minus e to the negative at times z to negative 1. Here's 1. Okay, so we will try to use capital HD, use this one for capital HD. But we need a scale. By this way, we have same impulse, not same. The impulse HD, the impulse response. This impulse response HD, it is symbols of HC. So if you look at the graph, they looks similar, like this. Then you go to here. Then you have the frequency response. How about the difference between these two frequency response? Are they same? Are they similar? Things like that. So actually, if you want they are similar, you need remember when we take sample, we have this x of n and xc of t. Remember, we take sample, we take xn from xc. Then this one, by Fourier transform, we will have 1 over t summation xc of j omega minus 2k pi over t, right? Things look like this. X omega this one. So I have 1 over t in front of it. So this one, if we do the not inverse, just z transform, I'm sorry. If we do the Fourier transform, we will get this one in frequency domain, this one in frequency domain, but divided by t. If I want these two are same, then I need to put a t in front of it. Okay, so this is the method. If hc of s is this one, we use this one to replace it. These two, they will have the impulse response, this one and this one respectively. So they are not same. But if we go to the frequency domain, these two should be same or similar. Okay, so the method is like this. hc of s, you do partial fraction. We have summation of s plus ai in the denominator. Numerator is some constant, I say ai. And then we have hd of z. It is summation of ai. Okay, here's s plus ai were replaced by 1 minus e to the negative at times z to negative 1. and I also need a times t here. I run from 1 to some. It depends, right? Depending on the order of the system. Okay, so method just looks like this. The same method. Not same method. This is the first method. Okay, this is the first method. It calls impulse invariance. Not exactly invariance. You need times t here. This is method 1. And the second method, we call this is a bilinear approximation method. We have edge of S, the continuous case. Then we get HD, discrete time 1, or I use Z. Okay, HD of Z. HD of Z will equal to HC of S. I replace this S by 2 over T times 1 minus Z to negative 1 and 1 plus Z to negative 1. That's it. This is the method. Okay, why we can work like this? We think the problem is like this one. If here is a 1 over S, if HC is 1 over S, then we have 1 over S. This side, if it is X of T, this side is Y of T. I can use, this is not the final output of the whole system. This is just part. If H of C has a 1 over S part. So for this 1 over S part, input is XT, output is Y of T. Then what are the relations? This should be the, if this side is a derivative, like this is a R dot of T, this side will be R of T. If this is some like a U, some V of T, this side will be integral of V of T. Okay? Things like that, right? This is derivative, then you have R. This is just any signal V, then here is integral of V. So this is just integration, this is interval. Then we have Y of T is integral from some future time, some past time. I just say negative infinite. Okay, until time t. Then here is x tau d tau. Right, we have this one. And this side we have a discrete time signal. There will be a symbol of it. So x of t according to x of n, which is x of n times t, and y of t according to y of n, which is y of nt. We have this. So we have y of n. Actually, it is. I put C here. It's a little bit complicated. I put C here. Then C here. Then no C is a discrete time. Then put C here. This is C here. No C, and here with a C. Alright. Y of n is yc of nt. It is an integral from 0 to nt xc. Right, look at this. If this is a xc of t, then the area, this is a yc of nt. If here is a nt, t equal to nt. The integral is just the area below the curve, right? Okay, then you consider next step. Y of n plus 1. it is also integral, but from negative infinity to this part. So you have one more. We have more areas like here. So this one will equal to integral from negative infinity to n plus 1 times t. It will equal to negative infinity. Here's a xc of tau d tau. Infinity to n plus from nt to n plus 1t. We have this. So y of n plus 1 equal to, what is this part? This part, it is just the y of n, right? Yeah, y of n, n plus this part. What is this part? So this is y of n plus the area of this part. I just use graph to represent. And here's a t equal to n t, and here's a t equal to nt plus t. Alright, now what is this area? We think this area, we can replace it by the rectangle, right? The rectangle and this, the whole area, they are quite close. The difference is very limited. And this side is x of n, and this side is x of n plus t, plus 1, right? That means in continuous time is plus t. Now in discrete time is n plus 1. And here will be the middle. So this is a x of n plus x of n plus 1 over 2. Okay, we use this value times the length of the interval, we get the area. So this part, actually it will be x of n plus x of n plus 1 over 2 times the length here is what? It is 1, right? It is a t, right? It is a t. The length is t. Every t we take a sample, right? The length is t, nt to nt plus t. Okay, this area is this one. So we have y of n plus 1 equal to yn plus this one. So we have the relation between y and yz over xz is what? We move the term y together. So this is 1 minus z to negative 1. And x term is t over 2, n plus 1 is just n plus 1. And this is 1 delay. So plus t over 2 z to negative 1. So it is t over 2 times 1 plus z to negative 1 and 1 minus z to negative 1. Okay, and what is this according to in the C area? That will be y of s over yc of s over xc of s, which is, we have our system is just 1 over s, right? It is 1 over s, so this is 1 over s. This is just 1 over s. Alright, we have our method. This one according to this one. Another word, s according to t over 2, now it's 2 over t. 2 over t is 1 minus z to negative 1 over 1 plus z to negative 1. Okay, so this is the second method. We just replace, you have h of s in the continuous time, you just replace s by this part, then you have a discrete time one. Okay, so this is second method. So actually we have more method, but here I just introduced you two. Alright. And then we will try to run MATLAB. In MATLAB, you can see the building function MATLAB, you can see more method there. Okay. Yeah. Example. We can try a field, we start a continuous times field, and then we transfer it to a discrete time one. We try this. We try HC of S equal to see like this. It's a s squared plus 5s plus 6 is a 6 over it. Alright, then this one I can write it as s plus 2 times s plus 3, here's a 6 over it. It will be s plus 2 over some a and s plus 3 over some b. What are a and b? So here a plus b, a times s plus b times s should be 0, because here we only have 6, right? Numerator only 6, no s. So as plus bs should be 0. And a times 3 and b times 2, and we get 6. Okay, so like just 6 and negative 6. Am I good? This is a 6s minus 6s is 0. 3 6 minus 2 6, I get 6. Okay, so HC is just this one. Then what is a HD? We want to find the discrete type. We choose a t. T is point like a 0.2. Yeah, you can try different value. T is this one. And then the HD of Z. I say this is the first one. I put the bar here. First one. This is by the impulse invariance. This one will be equal to, we just replace s plus 2 by 1 minus e to the negative 2t, then z to negative 1. Here's 6 times t, and minus 1 minus e to the negative 2t, negative 3t, this is 3, so negative 3t, z to negative 1. Here's a 6t. The h bar of z just looks like this. Can we make it put them together? Okay, I leave it. Okay. Yeah, you plug in all the value, you can do a calculation. You can do a calculation. And HD, I use a hat. This is for bilinear method. Then this one will be, okay, you just replace s by that one. So this is a 6 of, here's a s, replaced by 2 over t times 1 minus z to negative 1 over 1 plus z to negative 1, then plus 2. Yeah, it's plus 2. And times t. And minus 6 over 2 over t, 1 minus z to negative 1 over 1 plus z to negative 1, and plus 3, and times t here. Okay, so this is a HD hat. Okay, we can see the graph for the exact values. Using MATLAB to do the calculation. Okay, yeah, you can just plug in the value in, but that costs a lot of time. I already opened the MATLAB here. Okay, I open the file. Let me open file. This is 317. I open the file. It's edit of the. This is a lecture 14 Mondays class. All right. Okay, then I have this one. Then I have this one. Right. I can see the both. So firstly, we have HC. To determine a field in MATLAB, you need a numerator and denominator of the transfer function for both continuous or discrete time system. So here I have numerator for the continuous one, numerator C is just 6. All right, and the numerator. Denominator for continuous one, that is 1, 5, 6. Okay, so then we have HC. HC is the transfer function with numerator C and denominator C. So this will give us the continuous times field. And we also have HD. HD I have two, HD1, HD bar I use HD1 here. Okay, HD1. HD1 I also need a numerator. I have two. So I think we can work like this. It's I have T first. T equal to 0.02. Alright. And HD1, it will be okay. For discrete time we need a field. The numerator is 6 times T, and the denominator is 1, and the negative exponential power of negative 2 times T. Okay, that's it. We can leave the calculation to the computer. Computer can do it. Right? Computer can do it. And minus another field. Numerator is still 6 times T, and the denominator is 1 minus exponential power of negative 3 times T. Okay, am I good? Numerator, denominator. Oh, here's I need a square blank, and here's here I need a still square blank. Okay, I think this works. Did this work? Let me try. F5. F5, save it, yes. Okay, nothing wrong, so it works. I have HC and HD1. Okay, we have both, right? We have both. The computer do the calculation. And we can also have second one, HD hat. HD I use HD2 for it. HD2 is okay. So here this is just replace. This is a lot. Okay, I work like this. We can use algebraic one to work on it. I define this z equal to, z is a transfer function with z with a step. I think I need a step t. Step is t. Did this work? F5. Okay, yeah, I define the z, right? I define the z. Okay, I define z. After I have a z, I have a z as s, from s transfer to z. This one is 2 over t times 1 minus z to negative 1. Okay, just z minus 1, right? Z minus 1. Z minus 1 over z plus 1. Are they same? This part, 1 minus this one, over this fraction, right? Z to negative 1. I times z on both numerator denominator, then to be z minus 1, z plus 1. Okay, so this is the sz. And then the HD2, HD hat, I use HD2. This is t times 6 over, both has a numerator, right? The same numerator. Okay, so just like this. This one over t over 2, that is sz. So it is sz plus 2. Okay, and minus t times 6 over, now is sz plus 3. Yeah, I leave all the calculation computer can do it. Right? HD. I should have HD. HD2. Yeah, I have HD2. Okay, so I have all of these three. One is HC, the original one, HD1 and HD2. They are discrete time one. Okay, we want to see how they looks like. I use some figure to see what it is. Figure 1. Okay, use a frequency response. Figure 1, hold on. Then I can put two pictures on it. A board of HS and a board of HD1 and the board of I missed a D. Board of HD2. Okay, I can run this. Something wrong. HS undefined function of variable HS HC. Sorry. HC. You know what? Okay. I need a T. I need to give a T here. HD, the field, I have numerator, I have denominator, but I didn't mention T. Let me mention the step here. I need to mention the step because I need to compare with the continuous one, so I need to mention the T, so they can have the same step to work on. Let me close. What happened for figure, like we can see the step response. Figure 2, also hold on. We see the step response. Can we see what happened in the step response? HC and the step of HD1 and the step of HD2. Okay. I have two graphs. I think there's something wrong because the unit problem. Some unit problem. 6T, and T. This is a field, and this is a bilinear. So bilinear it should be the green one. Bilinear is which one? Bilinear is the green one. Yeah, this green one, bilinear. In the beginning, it's wrong from a negative value, but finally they tend to the same value, right? And for the this is not bilinear. Green one is HD1. HD1 is what? HD1 is impulse invariance, right? H1 is HD1. And the second one is bilinear. See the bilinear? Bilinear. I need a. I tell you T. I got something wrong. Bilinear. Sorry. That's my fault. Yeah, I got something. I just think something wrong. The bilinear one. Bilinear just replace this S. So here I don't need this T. Right? Replace S by this one. So I don't need this T. Okay, HD I need to remove that. So that is H2. H2 I need for H2 I don't need this T. Okay. Let me run it again. Okay, this is bilinear one is quite good, right? See, the step response is quite good. And figure 1, the red one should be bilinear one. So the phase, you see, for lower frequency is quite close, and when the frequency for the magnitude also very close for low frequency part. For high frequency is not so exactly same, but it's not bad. And the green one, oh, do I have some mistake in the green one? It should be green one is this one, right? Green one is this one. We have a step 6 e to the negative t, negative 3t. 1 minus e to negative 2t, and 1 minus e to the, oh, here, yeah, that's this one. Yeah, that's totally different. Sorry. And okay, this time should be better. Run. Yeah, I can add these. Okay, you see, for the step response, the both two, the red and the green, they are the digital one, right? The green, the blue one, is the analog one. They are quite close, quite not exactly same, but it is fine. And for figure 1 in the spectrum, then for lower frequency part, they are quite similar. But when frequency tend to be higher, they have more and more different. So the red one here, they have a big gap, and the green one, they have less gap. Which green one is the impulse invariance, right? Green one is the impulse impulse invariance. The red one is the bilinear one. Let me try the red one is bilinear one. Now I can only see the bilinear one of the magnitude. Yeah, the bilinear one is going down with a little bit longer, large values. And yeah, okay. So different method, and actually we have more method. We have a function, and let me run here. Like we have HC, right? We have HC. HC is a continuous times system. HC, right? HC, and we can use that one. I can use I say G. G is C to D. Okay, this is a building function of MATLAB. Then you give the HC, the given continuous time system, and give time t, and then you can give the method. The method here is just t, just the t. T is for bilinear, and our HD2, is bilinear. Oh, this is not HD2. 6 over 15. 6 over 15, 6. You see? The result, we calculated this one. And this is given by the MATLAB function, is this one. Actually, this should be same. This should be same. We can calculate like HD2 over that G. You get the same one. It's 1, right? But MATLAB didn't cancel the numerator denominator. You get 1. These two are same thing. Right? Yeah. So you can also use the MATLAB function. Use this one to get the bilinear one. Bilinear. This is bilinear. T is let me see. Help. C to D. They give list of functions. No T. Yeah, it's a C to D, then system, then step, then the method. Method should be 0 or whole. Oh, it's here, bilinear. Bilinear is a testing method. Testing, so I can put T, right? Testing method. And some other method. They are similar with this one. similar. And they also have a matched one. Matched one is a matched pole and 0. And our impulse invariant method just match on pole. This is a method similar with that, but matched on both pole and zeros. If you are interested, you can try all of these different methods to transfer a continuous time system to be a discrete time system. Alright. Okay, that's all for today. Then see you next time. Bye bye.